Hello, everyone. Thank you for coming. The next talk will be about Mimi.jl, the next generation climate economics modeling. This talk will be given by Lisa Rennels, a PhD student at UC Berkeley, and Cora Kingdon, a research assistant at Resources for the Future. Please help me welcome Lisa and Cora.
All right. Hi, I'm Lisa. Thanks for the introduction. As she said, I'm a PhD student at UC Berkeley in David Anthoff's lab, and I work at the intersection of climate change economics and computer science.
Hi, everyone. I'm Cora Kingdon. I'm a research assistant at Resources for the Future, which is a think tank in Washington, D.C. that does environmental economics research. And today we're going to be talking about Mimi.jl, which is a Julia package originally created by David Anthoff, who's also here. And it's currently being developed by researchers at UC Berkeley and Resources for the Future. So today we're going to start off with some background about what is integrated assessment modeling and why it's important, and then a little bit of overview of the Mimi platform. And then we'll do a deeper dive into some of the design details of our platform, and we'll finish talking about some of the application, adoption, and impacts. So for background, Mimi is a Julia package for creating, running, and performing analysis on integrated assessment models, or IAMs for short. So integrated assessment modeling is a type of numerical scientific modeling that integrates knowledge from two or more domains into a single framework. So that's a pretty broad definition, but one highly relevant use for IAMs is to integrate projections of future physical impacts from climate change with economic impacts expected to result in the future. So IAMs are used to inform a wide range of policy decisions, including those dependent on the social cost of carbon, which is something I will briefly explain. So the social cost of carbon, or the SCC for short, is a metric used by the US government in cost-benefit analysis to represent the net economic effects of emitting 1 additional ton of CO2 into the atmosphere. So this value is calculated by running an integrated assessment model with an additional pulse of emissions and seeing what the additional economic impact from climate change would be. So this dollar value informs billions of dollars of rulemaking decisions at the federal, state, and local levels of government in the United States and abroad. And one important example of that is the Clean Power Plan, which was the Obama administration's landmark climate change legislation. And the expected benefits of that policy were in part calculated using the social cost of carbon. So the way that type of policy analysis works is that the Clean Power Plan was expected to reduce greenhouse gas emissions by some number of tons. And then the social cost of carbon is the metric that gets used to transform the estimate of emissions reductions into a dollar estimate of the benefits to the economy. So since the SCC is such a highly influential number in the policymaking process, the process by which it's calculated using integrated assessment models has attracted a lot of attention at high levels of government. So for some more background, here's a brief timeline of the modeling process used by the United States government for calculating social cost of carbon. So under the Obama administration, in 2010, the EPA began using 3 prominent integrated assessment models from the academic literature to calculate the social cost of carbon. And prior to that effort, different government agencies were using different numbers for the social cost of carbon in their regulatory analyses. So this was a very important step forward to have a standardized modeling process. The process, however, received a lot of criticism, and there was clearly a lot of room for improvement. So in 2016, the White House commissioned the National Academy of Sciences to write a report on how best to improve and update the modeling process for the social cost of carbon. So in 2017, that report was published. And one central recommendation from the report was to create an open source modular computational platform to better serve the modeling work in this area. So our team has created the Mimi framework, which is the leading and we think the only implementation following this specific call to action. So what is Mimi? Mimi is a software platform fully implemented in Julia. It's a registered Julia package. And so broadly speaking, Mimi provides a wide range of capabilities for two main types of users. The first being developers of new models or components of models, and the second being researchers who want to run or maybe modify or perform different analyses on the existing integrated assessment models. So with these two types of users in mind, we've worked to make Mimi very accessible and useful for both of these cases, and we'll talk more about those capabilities in a moment. I'm just also going to mention that the Mimi framework is also a community for fostering collaboration between developers and users of IAMs. So all of our stuff is open source on GitHub, where we're very responsive to issues and pull requests, and we also monitor an active forum for answering questions from our users and getting feedback.
All right, so now we're going to dive a little bit into some of the design decisions that we've made for Mimi. So some of the requirements that we had included that we needed something computationally fast. These models are very big and often run for long time horizons. And also, as we'll discuss a little bit later, they're often used in larger Monte Carlo analyses, which means not only do we have to run it once, we actually have to run it hundreds of thousands of times. So Julia's speed and performance is helpful for that. And we also needed something simple enough for novice programmers. Some of these models were previously written in Excel. Some were written in more complex languages, but in general, we needed something that users weren't scared off by. We also wanted something that worked with the pre-existing ecosystem of models. So as Cora said, the EPA is already using 3. There were several that were already in existence when we started this project, so we had to kind of create our platform around the existing models. So this led to quite a few different design decisions, 2 of which were, one, choosing to use a macro-based domain-specific language, and the other really informed our API, which uses a lot of multiple dispatch under the hood to keep the number of functions low and to make it easy to use, while under the hood we're abstracting away and taking care of data storage, performance optimization, passing data between things, that kind of thing. So quickly to review the structure of an integrated assessment model. So these models are modular, meaning that they are dealing with lots of different building blocks that are then connected together. And those building blocks are referred to in Mimi and in the integrated assessment community as components. So here you have an example of what some of those components might be. The all capital words are several existing integrated assessment models. So FUND, DICE, RICE, these are all existing models. So for example, you might have one component that handles climate dynamics. So it looks at how the climate's changing and how that affects temperature. You might have another that handles economic impacts. You might have one that specifically deals with sea level rise or the carbon cycle. And then when you create a model, you kind of tie a bow around a couple of these, make connections between them, and then at the end, your model outputs values that help answer some of the questions that Cora was talking about in the beginning, including calculating the social cost of carbon. So the structure of a component itself is pretty simple. You've got a list of parameters that come in. You've got code within the component that runs for each time step and computes things, and you have a list of variables that come out. And we will discuss in a moment that Mimi uses a macro called defcomp to define a component to easily define these blocks. And one of the most important things here is that the macro-based platform imposes a certain structure on these components, which allows us to both make assumptions that allow for the abstraction and connecting them together, but it also allows for easy composition of these components, especially from different groups of developers. So if we can assume certain things, it makes it much easier for us to put them together and make it modular, which was one of the main recommendations of the National Academies of Sciences report. So this code, I think, is a little hard to read, but it's what a typical defined component macro might look like from a user's point of view. So as I described, we have a set of variables, we have a set of parameters, and then we have this run time step function, which is a function that's inherent to every component and basically defines the main computations that happen in that component. And one of the most powerful things here is that we haven't hidden the mathematical formulas under layers of infrastructure code. They're right up front. This is really useful because a lot of the times you're writing these components straight from academic literature, so you want to be able to very easily see what the mathematical equations are. Also very useful for debugging or for other users to adopt your code or understand what's going on. So as I said, the next thing you do is once you compose these models, once you create these components, you want to compose a model. That basically says now that you have a bunch of components, you need to connect those components together. So this orange box would refer to a model. We've got some parameters coming into the model from the outside, like carbon emissions, carbon dioxide emissions, and climate sensitivity. And then we also have a parameter that's going from one component to the other. So under the hood, we carry out a lot of the actual work of managing data storage, the data structures, calculating values, and then passing values between components. And again, we use these macros and a simple API to make that easier for users. So that API looks something like this for creating a model. So first, here we create an empty model M. We then set dimension. Basically, all these models need some sort of time dimension. So here we're saying we want the model to run from 2000 to 2300 at 10-year time intervals. And then we add some components. So we've used defcomp to define all of these components already. And then we connect some parameters. So the connect parameter call is used to connect parameters from one component to the other. So for example, here what's happening is that the gross economy component's emissions variable is getting passed to the carbon dioxide cycles emissions variable. So these types of connections are very common. And this isn't the full API, but this is just a small example. So another really important feature of this project is easily allowing users to access and analyze their results. It's important for publication, for debugging, and also a lot of time you kind of want to work dynamically. So change something, see what happens to the results. So we've implemented some graphical tools to make that easier, as well as tabular get index, get data frame type calls. So for example, here we have plot component graph. So if you run a model and then you want to see the graph of what the components look like, you would make this call and you would get a graph like this. So basically this is showing all the circles or components, and then the arrows are showing which components are connected to which. And these can get rather complicated looking, but it's good like high-level overview for what your model looks like. Another thing that we've implemented is explore. So we call it the explorer. The function is explore. And basically what this does is you call explore, you get it's a little light, but you get an app window that pops up, and it allows you to interactively look at the values for all your parameters and variables for every component. This runs mostly on the vegalite.jl package and has been a really powerful, helpful thing for users, we've found. And then we've also added methods, get index methods and get data frame methods to help get the tabular data out of the more complex underlying data structures in the model.
Okay, so now I'm going to talk about a more advanced feature in Mimi, which is the ability to run Monte Carlo simulations and other types of sensitivity analysis. So this is very important because a lot of parameter spaces in both climate science and economic modeling are highly uncertain. So Monte Carlo simulations allow us to run thousands of trials of our model sampling from this uncertain space. So for defining a simulation in Mimi, we also provide a user-friendly macro. So here's an example of what that could look like. The macros function is called @defsim, and in the body of the definition, you'll notice you just use normal Julia syntax from the distributions package. So on the left-hand side of each of these assignments is a parameter name in the model that you're planning to run the simulation over. And on the right-hand side is just the distribution of values from which you want to sample. And in this simple example, it would just be using random sampling, but we also have more sophisticated support for methods such as Latin hypercube sampling and Sobel analysis. So here's a high-level diagram illustrating how to then run the simulation in Mimi. So we have our model here on the right and our simulation definition on the left, and we just pass both of these objects to the run sim function. And then Mimi runs the simulation for the user, which means that it's taking care of actually sampling all of the trial data and then applying all of the trial data to the relevant model parameters before each run of the model. And then it takes care of storing the desired output. So the main takeaway here is that Mimi really provides this layer of abstractions that the user just has to specify what they want the model and the simulation to do without having to worry about the more complex data storage and infrastructure required to actually run it. So another primary design consideration was that we needed a platform that enables a modular work style for distributed, loosely coordinated teams so that people on different sides of the country could be working on different parts of a model and be able to link them together. And we also needed a platform that creates a transparent framework enabling easy replication of computational experiments. So this led to our decision to create a custom Julia registry. And also we make sure that our workflow leverages the full power of the Julia package and project environments. So as I said, we created a custom Julia registry called the Mimi registry. So for convenience, many existing integrated assessment models are already registered in the Mimi registry, and they operate as packages with the Julia package manager. So what this means is that it's very easy for users to download and use the existing models using the Julia package manager without having to use Git or even knowing what GitHub is. So here is literally 2 lines of code in the package REPL showing how you can download the Mimi DICE 2010 model. So I'll just mention that DICE is a popular IAM that was developed by the economist Dr. Nordhaus, and it's been used to inform social cost of carbon estimates by the US government, and we have recoded this model in Julia on the Mimi platform. So the first line of code here adds our Mimi registry, and you would only have to run this line once on your computer, and then you'd be able to add any of our available packages by name as shown here. And so once the user has downloaded an existing package, many of these model packages implement a few standard functions for accessing the default versions of these models. So I'll show an example here. So if you've already added Mimi DICE 2010, then the third line, you call the get model function, and that returns the default version of Mimi DICE 2010, which is shown here as a 9-component model. And then you can run this model. And then at that point, you would be able to access any of the results in the way that Lisa already showed. And then I'll just also mention that the model packages that have been used to calculate the social cost of carbon, most of them also implement this compute SCC function. So what that does here on the last line is just for the model M that we already have, compute the social cost of carbon for the year 2025, which is shown here as $27. So one more design feature we want to explain is our workflow with Julia environments. So our vision for this framework is really that by using the package management system and Julia environments, users should be able to write academic papers that use these IAMs that are open source, transparent, and fully replicable. So this becomes increasingly important as we release new versions of our models, which are Julia packages, so that if you're working on a project that uses these models, we really encourage people to use a Julia environment so that in the future that work would be exactly replicable on the older versions of the models. And we think that this would be a huge improvement to specifically the EPA's modeling process for calculating the social cost of carbon. Because previously, as Lisa mentioned, there were 3 different models that were written in different languages, and one of them wasn't publicly available. So having all these models on one framework where you can easily stabilize the versions, it will greatly improve the transparency and accessibility of this modeling process, which is highly relevant for policymaking.
Great. So now for applications, adoptions, and impacts. So as we said in the beginning, one of the, I think, coolest things about this project that it is a very high impact, high visibility project that's been gaining a lot of traction with partners within and without and outside of the country. So there has been significant uptake of the Mimi framework for integrated assessment modeling. Our team manages some of these models, and then some of them are managed by other teams, but we advise them. So this is a list of all of them. This includes Fund, Page, and DICE, and these are the 3 that were used by the EPA for their social cost of carbon and are still being used currently by the EPA, as well as several others, some of which focus more specifically on improving one component or the other. So they might modify an existing model. Some might focus on things like sea level rise or improving ice sheet. I think Page Ice looks at ice sheet dynamics. Mimi Brick is something that's looking more closely at sea level rise. So it kind of allows people to take a model and then kind of play with a part and enhance it. We have someone at Princeton adding migration to one of them. So it's these kinds of like small additions that people can do that we've been able to enable. And so the adoption has happened at universities, at think tanks, and also abroad, the government level. So in terms of universities, obviously this is housed primarily at UC Berkeley at the Anthoff lab. We also have connections at UC Davis, Princeton, Penn State, LSE, and a few others. And then also, of course, working with Resources for the Future. And then most recently, because of our German professor and German connections, we've been talking to the German government, or at least looking at helping the German government with the value that they'll use if they put a carbon tax on the ballot in the future. So that's not going on right now, but it's something that we might be interested in doing in the future. We also recently presented at a conference in Tahoe. We did a one-day workshop with about 50 environmental economists at the ARE conference in Tahoe. And that really helped kind of grow our user base, increase visibility, and also give us feedback on the user experience. And so that was really helpful. So we're really hopeful that this will help power the next generation of US federal climate economics work in the regulatory space, but not only at the federal level, but the state level, the municipal level, and also in the private sector. Social cost of carbon can be used by companies that are taking a look at their own carbon impact, thinking about offsets, things like that. And we'd like to acknowledge the Resources for the Future Social Cost of Carbon Initiative, which has organized this dual effort and has been generously funded by the Sloan Foundation for the past about 18 months or so. Yeah. Now we'll do Q&A.
I'll join for Q&A.
So now please free to ask any question that you may have. Could you come? Yes.
That was a very nice presentation. I learned a lot. Thank you. When some of the models that said were private, or what is that, private to whom?
So it's up to the developer of the model whether they want to make it public or private. So it might be a private GitHub repository. Our lab's rule is that if we haven't published a paper with the model that we're working on, we generally don't make it available to the public. But for example, right now, the 3 models that the EPA use, those are all public. So it's not, we don't basically discern from our registry. We don't say it has to be public. Yeah, is that about right?
Closed? Yeah, so that's what Lisa just said. So closed just means right now you don't have access. It's not open right now. But I think all of these are examples where people are preparing submissions to journals, and as soon as the paper is published, the repository will be made public.
Yeah. And in a lot of these cases, we've had people contact us about closed models, and we've given them access to help us work on them. So it's normally a pretty collaborative environment. But again, sometimes they're closed if people are still working on publications.
Another question. You decided to use a domain-specific language for your model creation. You also went on and did the same thing for the Monte Carlo. Why did you pull the Monte Carlo into that as opposed to considering that an orthogonal connection of capabilities, like using an external Monte Carlo package applied to your system so that if there was more capabilities there, you could leverage those?
Yeah, so I'm trying to think of what's a good answer to that?
So I think one point is that we're actually reusing a lot of capabilities from other packages. And for example, all the Sobel analysis that we're using is published as a separate package. So if you want to use that, you don't have to buy into this Mimi story. And what this macro for the simulation does is it just pulls it together for really novice users, because that's sort of one primary target audience for us. I don't know how many of you are familiar with the programming skills of economists, but they're great. So we really, so there's a lot of value in us taking things that exist in other packages and then putting a very thin layer on top of it that makes it easier to integrate with the rest of the ecosystem that we have. And I think that's how I think about this DefSim simulation framework.
Yeah, but some of the sampling and the more complex things that are going on with the simulations are actually making calls out to a different package that we've written.
I'm just
Curious, how did it get its name, and is there a significance with that?
You're the only one that can answer that question.
There was it's unclear. The two colleagues of mine and I had dinner, and the name emerged. But memories are hazy.
That's what the website says too. So really, no one knows. It's gone from an acronym to a name because no one knows. We tried to come up with it last night, but we think model and integrated are probably in there, but we're really not sure.
So seems like a very nice piece of work. I was wondering, similar to previous questions, but in the other direction, a lot of it seems to be very general and applicable in many other modeling contexts than Julia. So to what extent can people use what you've developed for reproducibility or whatever in other contexts?
Yeah, that's a good point. I think there's actually nothing in Mimi that is specific to climate or econ. It does target a certain structure that happens to be used in those fields, and we were pretty focused. I think that sort of was one thing we tried hard to. We had a clear audience, right? So these kinds of, this is the fields we want to help. What came out of that, I think, could be useful in other fields. I could easily see that. And I think that would be great if people want to take it up. I don't know whether it applies to everything, probably not, right? But you're entirely right? This is, we came from one corner of the field, but I think what we created is probably useful for many other places as well.
I mean, you seem to just have a sort of way of connecting components together, and it's just a very general thing to do. You know, there have been various talks about modeling frameworks and stuff that it seems like, people outside your field might be very interested in that. And it'd be good to make that more widely known.
Right? So in that list that I just clicked through all my slides to find and didn't, there's a model I think called AWASH that and he actually works on climate models as well, but that's a hydrological model. So I think that's another application that I've seen quite similar, is those like kind of biological stepping processes. Yeah.
Thank you. Okay. Thank you very much.